Hello everyone, welcome to the fourth video in this series. In this video we will discuss the problems from 31 to 40. So let us start with problem number 31. Radii of two spherical atoms A and B are A and RB respectively. The lattice constant of the alloy AB if it crystallizes in a BCC structure will be. So let us remember the BCC structure. So in this lattice, each of the side has length A, and in the BCC structure we have atoms in every corner of the lattice as well as at the center of it. So this atom has radius RA, and this has also the radius RA, and the atom located at the center has radius RB. So now we find the distance of the principal diagonal. So this is RA, this is RB, this is RB, and this is RA. So we have 2 times RA plus RB is equal to square root of 3 times A, or A is equal to this divided by square root of 3. So option B is the correct answer. Problem 32. In a lithium atom, the outer electron is replaced by Me1, which has same charge but roughly 200 times heavier. The chemical properties of the resultant atom would be. It took some time to figure out what the correct answer is. I found this article, it's called Negative Muon Chemistry by Posada et al. So the authors wrote in their resultant discussion section, it is common practice to assume that the electronic properties of a muonic atom with atomic number Z are identical to those of a regular atom with atomic number Z-1 as a result of the muon perfect screening of a positive nuclear charge. So this is enough to answer our question, but let's move on to the table 3 in that paper. So here we can see helium has the ionization potential of 24.587 electron volt. And on the other hand, the lithium muon atom has the ionization potential as 24.526. So these two are very similar to each other. Whereas the lithium, the regular lithium, has the ionization potential 5.392. So let's move on to the options. Very similar to helium, so this would be the correct answer. Problem 33. Balmer series of the spectral lines of hydrogen atom consist of transition of electron from a state with principal quantum number n greater than 2 to a state with n equal to 2. So let us recall the fine structure corrections are proportional to alpha to the power 4, where alpha is the fine structure constant. And due to these corrections, the hydrogen atom energy levels now depends on both the principal quantum number n and the total spin j, where j is L plus s, where L is the orbital angular momentum and s is the spin angular momentum. Now this energy levels n equal to 2 now splits into 2 parts. Let's see how. N equal to 2 means L is 0 or 1. We have the spin angular momentum is equal to half. So let us add L plus S. So when L is equal to 0 and S is half, the total angular momentum is half. But when L is equal to 1 and S equal to half, then J could be 3 by 2 or half. So we have two distinct values of J. So that's why this N equal to 2 state splits into 2 parts. Similarly, N equal to 3 state splits into 3 parts. Now the transition from higher energy level to the lower energy level are possible. So there could be 6 such transitions. So initially a single line from N equal to 3 to N equal to 2 now splits into 6 parts. So let us come back to the options. So we do not see any option with 6 lines. So I'll leave it here and I'll let you figure out what the correct answer is. Problem 34. Laser cooling of atoms is produced due to. So laser cooling is a technique that uses the photon's momenta to restrict the atom's thermal motion. So the photon is absorbed by the atom and a new photon is re-emitted. So due to this change of momentum of the atom ceases to move. As a result, it cools down. So let us look at the options. So absorptions by photon by atoms, that is true. Scattering of photons by atom, that is also true. Transfer of momentum from photons to atom, this is also true as well. Transfer of energy from photon to atoms, so this is also true. So all the 4 options here are correct. Problem 35. What is the degeneracy of an orthohelium atom in minimum energy state? So in the ground state of orthohelium atom, the 2 electrons are parallel to each other. That means the total spin of the 2 electrons is 1. So there are 3 states that has the total spin is equal to 1. This state forms a triplet state. So the degeneracy would be 3. So option A is the correct answer. Problem 36. If a proton were 10 times lighter, then the binding energy of the electron in a hydrogen atom would have been. Note that the binding energy of an electron in hydrogen atom is same as the ionization energy of an electron. So let us recall. The ionization energy of an electron is Hc times Rydberg constant. The Rydberg constant is equal to m e to the power 4 by 8 epsilon 0 square h square. So this m is the mass of the electron. So in this case we assume that the proton is stable, it does not move. But if we assume that proton is mobile, then we have to use our heavy, and let's call it by 1, where this electron mass is replaced by the reduced mass of electron and proton. So this can be written as R infinity times mu by m. So this is equal to R infinity m, capital M is the mass of the proton, divided by m plus m times m. So this m cancels out. So now we have a proton that is 10 times lighter. So RH2 is R infinity times 0.1 m divided by m plus 0.1 m. So let's compare these two quantity. So RH2 divided by RH1 is equal to 0.1 m divided by m plus 0.1 m times m plus m divided by m. This capital M cancels out. Now we assume that the proton mass is 2000 times larger than the electron mass. This is a good approximation. Now we find this is equal to 0.1 times 1 plus 2000 divided by 1 plus 200. And this is equal to 200.1 divided by 201, and this is certainly less than 1. So we find that the Rydberg constant when proton is 10 times lighter is less than the usual Rydberg constant. Now if you try to plot the energy level, so this is 0, and initially we have the energy of ionization energy at minus 13.6 electron volt. Now RH2 is slightly less than the previous one, so we have now the energy which is slightly higher. Now you can see the binding energy is less compared to the previous one. So let's go back to the options. So the binding energy of the electron in a hydrogen atom would have been less. Problem 37. Let X denote the eigenstate of an operator X corresponding to the eigenstate X. Then the state psi, which is equal to exponential of I A P divided by H bar, that acts on the gate X, is an eigenstate of X corresponding to the eigenvalue. So one of the way to solve this is to express this exponential in series. So we have psi is equal to e to the power I a p divided by h bar times x. So let us consider this. So we can write this exponential in series with n equal to 0 to infinity I a p divided by h bar and in factorial here. This can be simplified as I a by h bar in x p n x. Now somehow we have to translate this operator x through these p's and act on x. For this we use an identity, that is x p to the power n is equal to ni h bar p n minus 1 plus p n p to the power n x. So this summation splits into two terms. The first term is n equal to 0 to infinity 1 by n factorial I a h bar to the power n I h bar p n minus 1 x get plus n equal to 0 to infinity 1 by n factorial I a h bar whole to the power n, then p n x as an operator acts on the get. So this is, we know, x times x. So this x can be taken out of the summation. From this term we have x times get psi. Here n cancels out with n factorial and gives n minus 1 factorial. Then we take one factor of this quantity out. This can also be taken out. So we have n equal to 0 to infinity 1 by n minus 1 factorial, but note that n now only runs from 1 because we have already cancelled the leading term, times I a by h n minus 1 p to the power n minus 1 and x get. Now we shift n to n plus 1. So this time the new summation index m runs from 0 to infinity. Summed now becomes n factorial I a h bar to the power n p n x plus we already had psi, and the prefactor is now minus a. We recall this is get psi, so this simplifies as x minus a get psi. So the state psi is an eigenfunction of the position operator with eigenvalue x minus a. So option A is the correct answer. Problem 38. The critical coefficients of a van der Waals gas are, we know the equation of the van der Waals gas is given by P is equal to RT divided by V minus P minus A V squared. The critical coefficients of the van der Waals gas correspond to the inflection point of the graph in PV diagram. In other words, when these derivatives dP by dV and d2p by dv2 are simultaneously 0. So let us calculate the first derivative of pressure with respect to the volume, and this is equal to minus RT B minus B whole squared plus 2A by V cube. This has to be 0, and del 2P by del V2, and this is 2RT divided by V minus B whole cubed minus 6A V to the power 4 is equal to 0. So we can cancel 2 here. So we have to solve these two equations. So let us eliminate RT first. So from the first equation we can write 2A by V cubed is equal to RT divided by V minus B whole squared, and that can be written as V minus B times 3A by V to the power 4. V cubed cancelled here, so V only remains and A gets cancelled. So we have 2V is equal to 3V minus 3B, or V is equal to 3B. And let us find the temperature as well. So from the first equation we find RB, and here we put the value of V, that is 3B minus B all squared is equal to 2A by 27B cubed. So this simplifies to RT by 4B squared equal to 2A by 27B cubed, or T is equal to 8A divided by 27BR. So let's go back to the options. B is equal to 3B and TC is equal to 8A by 27BR. So option B is the correct answer. Problem 39. Consider a square lattice of lattice spacing A in 2 dimensions. That means this is A and this is also A. An electron of wave vector k is incident on a lattice plane parallel to the y-axis and making an angle theta. The electron will be Bragg reflected completely by all the planes parallel to both x and y-axis when. So assume that this is reflected from the y-axis. So that means the reflected wave vector would look like this. So delta k is equal to k prime minus k, and this is equal to minus 2 of k of x. Now using Law's equation, delta k dot a times x is equal to 2 pi h, and we can take the Miller index h is equal to 1. So we have minus 2 kx, a is equal to 2 pi. So we have kx is equal to minus pi by a. Similarly, when the wave vector is reflected from the x-axis in this way, this is now k prime. So delta k is equal to k prime minus k, and this is equal to minus 2 of x of y. So again using Law's equation, so minus 2 of y dot x of y is equal to 2 pi L is equal to 2 pi, or k of y is equal to minus pi by a. So if we see the options, option D is the correct answer. Problem 40. The fact that beta decay is due to a weak interaction can be inferred from the lifetime of the free neutron, because it almost takes 15 minutes for a free neutron to decay, and it is a characteristic of weak interaction that the lifetime can vary from 10 to the power minus 13 seconds to almost some hundreds of seconds. So option A is the correct answer.